Okay, let's jump right into this. We're looking at a story today that is just as fascinating as it is terrifying. It's a journey that starts with, of all things, a simple glowing rock in a Parisian laboratory, and it leads humanity to this profound crossroads. We were handed the terrifying power to completely destroy our world, or, well, maybe it's the ultimate tool to save it from climate catastrophe. Welcome to our explainer on the deeply complex history of nuclear power.
So, here's our roadmap. We'll be navigating over 120 years of history today. We'll start with the atomic dawn, move into the global arms race, trace the rise of nuclear power, confront the disasters and public backlash, and then wrap up by looking at the future of nuclear.
All right, part one, the atomic dawn, unlocking the universe. Picture this. It's the turn of the 20th century. Back in 1896, physicist Henri Becquerel accidentally discovers that uranium darkens a photographic plate without any light. He called them uranigrays. Over the next few decades, brilliant minds like Pierre and Marie Curie and Ernest Rutherford realized that atoms aren't actually indestructible. Fast forward to 1938, and Hahn and Strassmann pull off the unthinkable. They discover nuclear fission by literally splitting a uranium atom in two. Just a year later, Giulio Curie proves this can cause a chain reaction, and then bam, by 1942, Enrico Fermi successfully controls the first atomic pile. It's just the stunning exponential curve of scientific discovery.
But, as World War II breaks out, this pure science gets weaponized. After getting a warning letter from Albert Einstein about Germany's research, the US launches the top-secret Manhattan Project. Now, to build a bomb, you absolutely need a chain reaction. But they faced a monumental engineering hurdle. In nature, over 99% of uranium is uranium-238. Only a microscopic 0.7% is the fissile uranium-235 that you actually need to trigger a bomb. So the immense challenge for the US, Canada, and the UK was figuring out how to isolate and concentrate that tiny, tiny sliver to create highly enriched uranium.
Which brings us to Section 2, the global arms race, the apocalyptic pivot.
And just like that, the theoretical rapidly became apocalyptic. On July 16, 1945, the first nuclear test succeeded in New Mexico. Shortly after that, the United States dropped 2 atomic bombs, a uranium bomb on Hiroshima and a plutonium bomb on Nagasaki. 200,000. That is the sobering number of approximate civilian casualties from those 2 blasts alone. Days later, Japan surrendered, and honestly, the world had fundamentally changed forever.
After the war, the USSR really accelerated its own program, kicking off a frantic Cold War arms race. But the tech didn't just stop at fission. The arms race shifted from fission bombs, which work by splitting heavy atoms, to thermonuclear fusion bombs, or H-bombs. Fusion works by fusing light atoms, like deuterium and tritium, together under immense pressure and heat. It's literally replicating the terrifying power of stars. What's crazy is that to even achieve that necessary heat, they actually have to use a fission atomic bomb just as a trigger. The escalation of destructive capability that followed is, well, it's difficult to even comprehend. The Soviet Union responded to the US by testing the Tsar Bomba. That single test unleashed an unfathomable 50 to 57 megatons of TNT. To put that into perspective, the blast was exponentially more powerful than the bombs dropped in World War II. It marked a truly terrifying peak in humanity's ability to destroy itself. Tensions soon reached a boiling point. The US tested a bomb at such high altitude that it created an artificial aurora visible all the way from New Zealand and knocked out satellites. Wild, right? Then, the Cuban Missile Crisis brought the US and the USSR to the absolute brink of nuclear war over missile placements. This massive near miss finally forced global powers to negotiate. They drafted the Non-Proliferation Treaty, limiting weapons to the 5 existing major powers, and regions like Latin America declared themselves completely nuclear-free zones. However, several key nations, notably India, Pakistan, and Israel, abstained from signing entirely, or just maintained a stance of strategic ambiguity. All right, moving on to Section 3, the rise of nuclear power, harnessing the atom.
Fortunately, all this incredible energy wasn't meant exclusively for destruction. Scientists were simultaneously racing to harness it for massive electricity generation. Fast forward to 1973, and the world gets hit by a massive oil crisis. The price of a barrel of oil absolutely exploded, totally paralyzing economies that depended on it. This crisis directly triggered a massive global surge in building nuclear power plants. Nations like France and Japan, who were heavily reliant on imported oil, aggressively pivoted to nuclear power just to ensure their own energy independence.
Let's demystify the engineering behind these massive plants for a second. The essential steps of a pressurized water reactor, which is what makes up the majority of today's fleet, are surprisingly elegant. First, low-enriched uranium sits in a vessel, and the controlled chain reaction creates intense heat in a primary water circuit. That heat then transfers to a secondary circuit, rapidly turning water into steam. Next, that steam rotates a massive turbine linked to a generator, producing the electricity that powers our homes. And finally, a cooling circuit, usually drawing from a river or the sea, condenses the vapor back into water. It's an incredible cycle.
Section 4. Disasters and Public Backlash. Humanity's Hubris.
But as you might expect, humanity's confidence in safely controlling this immense power soon met with some catastrophic and deeply sobering realities. In 1979, the 3 Mile Island plant in the US experienced a core meltdown, though thankfully the containment held. But then, in 1986, technicians at Chernobyl in the USSR lost control. The resulting explosion literally blew the roof off the reactor, spreading a highly radioactive cloud across Europe, creating a 2,600 square kilometer exclusion zone and displacing 200,000 people. Then, in 2011, Japan suffered a 9.1 magnitude earthquake and a massive tsunami that overwhelmed the Fukushima plant, causing 4 reactors to explode. These events heavily braked global nuclear expansion, prompting countries like Germany to announce a complete phase-out.
And beyond those environmental disasters, there's the ongoing geopolitical anxiety of what we call the proliferation web. The quiet spread of nuclear technology remains a massive, massive concern. Take A.Q. Khan, the father of the Pakistani atomic bomb. He acknowledged running a clandestine network that supplied nuclear plans to Libya, Iran, and North Korea. Today, North Korea has withdrawn from treaties and conducted tests. Iran's uranium enrichment deeply worries the international community, and Israel continues to maintain its strategic ambiguity. The genie is well and truly out of the bottle.
So today, we find ourselves stuck in a massive environmental paradox when it comes to nuclear energy. On one hand, nuclear power emits incredibly little climate-damaging CO2 during operation. That makes it a hugely attractive option in our fight against global warming. But on the flip side, it leaves behind high-level radioactive waste. And current technologies just don't have a definitive, easy solution for this. We have to rely on deep geological storage for waste that will remain dangerously radioactive for hundreds of thousands of years. I mean, that vastly outlives our current civilization.
Which brings us to our final section, Part 5, the future of nuclear. Powering tomorrow.
As the modern push for clean energy heavily collides with our aging infrastructure, what exactly comes next? Let's look at the hard numbers. Currently, there are 417 operating reactors globally, providing just over 10% of the world's electricity. There are 46 under construction, mostly concentrated in growing economies like China. But the truly alarming reality is this. A massive 2/3 of the global nuclear fleet is already older than 30 years. They are nearing the end of their originally planned 40-year lifespans. That makes safe dismantling a looming, incredibly costly challenge for the world over the next couple of decades.
Hoping to solve the waste, the safety issues, and the fuel limitations of traditional fission, the world is actually looking back to the stars. 35 countries are currently pooling their resources into the ITR project over in France. It's this massive experimental facility attempting to finally commercialize nuclear fusion. Now, the budget has jumped astronomically from 5 to 19 billion euros. But if it works, it could produce virtually limitless electricity with incredibly little radioactive waste. It's a real game changer.
We have seen the atom end world wars, power entire modern cities, and, unfortunately, poison the Earth. It is literally the ultimate double-edged sword. All of this leaves us with one unavoidable, profound question to ponder as we figure out the future of global energy. Given its history of apocalyptic destruction and catastrophic disaster, is unlocking the power of the stars humanity's ultimate salvation or our final mistake? Thanks for joining us on this explainer. Keep questioning and keep learning.